Hello everyone. Let's have a class for the chapter 3. Let me share with you the PowerPoint presentation slide for the chapter 3. We are still at the chapter 3 um, in image enhancement by using a frequency domain. Previously, we learned image enhancements by spatial domain, which is the enhancement based on pixel values, direct manipulation of pixel values. But now we will look at another method of the image enhancement by using frequency domain. So image enhancements in frequency domain, as we learned from previous slide, enhancement is defined by making an image more valuable, as in value, desirability, or attractiveness. And frequency is a number of times that a periodic function repeats the same sequence of values during a unit variation of the independent variable. So these are the definition of image enhancement based on frequency domain. So any function that periodically repeats itself can be expressed as the sum of sinus and cosinus of different frequencies, each multiplied by a different coefficient. So the image enhancement based on frequency domain can be based on a few methods such as Fourier series, wavelet, Gabor, and a few other available technique or method for image enhancements based on frequency domain. Even functions that are not periodic but whose area under the curve is finite can be expressed as the integral of sines and or cosines multiplied by the weighting function and transform. The advent of digital computation and the discovery of fast Fourier transform algorithm in the late 1950s revolutionized the field of signal processing and allowed for the first time practical processing and meaningful interpretation of hosts of signals on exceptional human and industrial importance. So this signal processing or image processing based on frequency transform is started with the discovery of fast Fourier transform. So this is the guy who created the Fourier series, so that his algorithm was benefit a lot of people to analyze image as well as signal, starting from the signal and continue. So this is the guy, French mathematician and physicist. So the method Fourier is taken by his name Jean-Baptiste Joseph Fourier, 1768 until 1830. So this is the periodic signals, the denoted as a mathematical equation x t plus t equals to x. Fundamental period t naught of xt is smallest t, satisfying both equations. So this is the mathematical equation for a signal with certain frequency and angular frequency. So this is the predict signals looks like. You learn this a lot in digital signal processing, but in this image processing, when you're not study this two-dimensional, we are one-dimensional signal. We are looking into the two-dimensional, three-dimensional signal. So this is an application of signal in biology and medicine. It is used in ECG, measure of the dipole moment caused by depolarization and repolarization of heart muscle cells. Semitogenesis, a vertebrate body plan, a segmented pattern. Segmentation is established during somitogenesis, which is studied at Berkeley Lab. So this is also a signal. So Fourier transform is very useful and is used a lot in many scientific areas such as physics, signal processing, building image processing, probability theory, statistics, so on and so forth. Fourier transform in signal processing, audio and image signal processing. Audio and image signal are very light, one-dimensional or two-dimensional. Fourier transform is used for easier way to apply different kind of filter to the signal. Filters are used for removing noise from signal, altering signal. So if you look at the application of Fourier series, it is used in filter. So what is the function of filter? To remove noise, remove unwanted frequency, alter a signal. So this is all towards the enhancement. Type of Fourier series: expansion of continuous function into weighted sum of sines and cosines. So this is all the what do you call the family of Fourier. Fourier series, Fourier transform, discrete Fourier transform, and fast Fourier transform. This is four. This is the latest one, which is used in image processing. But this is all based on the mathematical equation of Fourier series. So this is the equation or mathematical formula for DFT, discrete Fourier transform. Summation of function exponential negative j 2 pi. Okay. If I'm not mistaken, in signal processing, you study detail, you learn detail this equation. Then you have to do all the mathematical calculation to get the frequency, for example, to get the value, final value. But in image processing, I'm not interested to go up to the details. But the most important is for you to understand frequency domain, especially Fourier transform. Not in detail until up to the mathematical equation, but you know how to implement how to use this Fourier transform into an image for image analysis. When you apply a Fourier series to an image, the output also in a form of image. I mean, it is a value, but you are not looking at into the value, because if you go to the single values of output DFT, or we call it DFT coefficient or FFT coefficient, you don't understand, because there are a lot of values depending to the size of image. So normally we are not going to the details study the single value of the output of the FT, but we visualize the output of the FT and try to uh, give explanation, or try to get some information based on the output of the FT. So this is an example of DFT when we apply to very simple image like this. All the background is black, then you got your object is white. Then when you apply DFT or Fourier transform, then you will get this kind of output. So we have to understand what is the meaning of this output in terms of DFT. Otherwise, you don't understand what is this. Why from this one single white object, then you get this a lot of white along the middle of the x and y axis. This actually represent or giving some meaning based on frequency domain or based on the. Okay, this is more practical example. Then you will appreciate where the DFT can be used, especially in engineering application. For example, if we have this scanning electron microscope image of an IC, then you will get this image when you magnify or when you use electron microscope, which is this one is a effect, this is the soldering of the IC, but due to the some defect, then the IC got some deep defect here. This is what vision system need to do the inspection to inspect any leakage of the IC connection. So when we apply the FT, we get this output. Let me explain you general meaning of this output. Since we are analyzed by using discrete Fourier transform, and this discrete Fourier transform is based on Fourier series, which is we intend to find frequency. So this output is actually represents some frequency of the image. Okay? It is not frequency like 50 hertz, like 250 hertz, where you found this in signal processing, but in image processing, we don't go to this detailed single value of frequency. But this is all frequency. Okay. There is a different way to analyze the output of the frequency of image when compared to the output of the frequency of signal. Because for the image, we don't look into this 50 hertz to 150 hertz, but we look at the output of the frequency, which is giving you a certain meaning or represent some information inside this Fourier spectrum. Features from an image can even sometimes be seen in the first spectrum of the image. Okay. Let's see the detailed definition of this output of frequency Fourier series or frequency domain or Fourier transform. Okay, but before that, let's have a look at this inverse DFT. We have inverse DFT, we have DFT, right? Then we inverse. Because this is image enhancement. When you inverse, you get a good image compared to the original image. Then the function of the FT is to to become like a filter, to remove all the unwanted, to to find uh, detail values. So when you remove the unwanted signal, when you inverse, then you will get a good signal without any disturbance of noise. So this is a formula of inverse Fourier transform. Right? Okay. So this block diagram is overall step how to enhance image by Fourier transform or based on frequency domain. So you have your image, then you perform pre-processing, okay, and then that pre-processing you choose a Fourier transform because you want to enhance the image based on Fourier transform. Apply Fourier transform, DFT, FFT, uh, you can choose any Fourier which can be used into an image. Okay, then you get the uh, output FUV here, output of Fourier transform. Okay, this output. So in order to enhance the image, you have to do something to the output of Fourier transform, because Fourier transform is about frequency. So in this one, output of the Fourier transform, you get the low frequency, high frequency, average frequency, a lot of frequency inside. So in order to enhance the image, you have to do something to the FUV, to the frequency or to the output of the transform. So one of the method, one of the approach is you apply filter to the Fourier transform, the output. Okay, the output of Fourier transform. Apply filter function. So filter function is that you remove all the unwanted signal, unwanted frequency, then you just retain the wanted frequency. Then you get this output. So in order to get the enhanced image, I mean original image but enhance it, then you apply inverse Fourier transform. Then after that you will get the enhanced image. Then you can perform some post pre-processing before you get the. So this is all the step in DFT for image enhancement. So this is an example where you can use Fourier transform for image enhancements. So this is all the detailed formula of Fourier transform, discrete time case, Fourier transform, its inverse. Okay. So this is all the mathematical formula. Then read it for yourself. Okay, so continue part 2. Thank you.